我的电脑的荧幕跟我的脸，然后这时候我再把我的 这边看看这边荧幕镜像输出 Brandy 的 MacBook Air，灯，然后就变这样。
那你版书这样来写是黑板的还是
这里？
哦，你都是这种数位版书的？
对，就在这边写。
哦，
然后它就会，你看它就只会看得到这个。
OK，那数位版书就是你要写的好啦，因为我经常会有那种版面不够的。
没问题，来这边你看这个啊，用 GoodNote 的这个东西，它就会写的很漂亮啊。对啊，
那如果你课程很长呢？
对啊，你会选很长，
嗯，
会选很长。
哦，那你真的是字蛮好看的。
没有用放大就放大就好了。
哦，
放大就好了。
好，
对啊，当然我知道你所谓的 equation 很长，可能是版面会很杂乱。
对，所以有时候我会把这个升上去，然后就是黑板这样写。
所以我一开始就会计划好，所以像刚刚这个地方，我就是发现写不下了，我就预设就是会多下一页，所以实际上我都是照抄我以前的，我都有一个小的叫什么笔记。
明白。
所以说你看这个其实我就是照抄上面的，你会发现几乎一模一样。
明白。
你看长一模一样，就这样。
是，
然后颜色都一样，所以其实上我都上课都不用思考，直接。
所以你现在完全都用不到实体黑板机？
我都用不到实体黑板。对
，OK，
这些我都有在我的 YouTube 频道都有，你可以上网看。
有，但我后来想一想，如果我在过几年开始录制后期大于，可能我现在锁那个观看者，因为我不想要重复，我不想要人家造神，我怕被防护，我太玻璃了。我会给你留个言啊什么的。
对，的确会有留言，像我的第一个留言就是这样讲的不太好，就是你要就是那种诈骗或者是非法的东西，这样我就把它删掉，这样。对啊，好，大概是这样。好，谢谢。冷气有开吗？
对啊，
好热哦。对啊，
这个人
对啊，温度。好，你可以帮我控管一下，如果还是很热，你就帮我调到2，谢谢。OK。啊，26、25，法律是28啦，但是你就调到2好了，我不知道，我不知道，好。OK，so 很漂亮，写的是很奇怪的词啊，从头来。OK，last time we talked about the shear stress in I-shape beams. Okay, and we said that we only it's only easy for this flange. Flange. Sorry, web. This is web. Only for web. Okay, because you can see the stress distribution is really complicated at the top and bottom flanges. Okay, so the Q VQ divided by IT, the Q only suitable for the place in between in this web. Okay, that's it. And then last time we said for I shape, you can use either blue shape, and then minus the negative or plus negative area, yellow, and then you can obtain the I, or you can do the solution 2, using parallel axis theory, you can move from the center of the top flange to the middle and move the bottom I to the middle. So you can obtain exactly the same value of the I, okay? And then we also multiply all these shear with area, and then you can obtain the shear stress and shear force, all right? And then now, this is a very kind of classic example. And then after you doing this, after you learn how to determine this example, and then pretty much you can know all the examples or problems in chapter 5. All right, so get ready. This position at this cross section has the V equal to 45 kN, which means that actually in the real problem, maybe you can obtain like this, and then you draw the shear and moment diagram, and you find that this position has V equal to 45. Okay, so we just tell you we ignore the chapter 4 things. Okay, we just obtain V equal to 45. Here V equal to 45. And what is the shear stress tau 1 at the top of the web level NN? What is NN? Okay, I will give you the NN point. Okay, NN point. Sorry. NN point. Okay, and we want to know the shear at this level. Okay, and this is called tau 1. This is called tau 1. So we want to obtain tau 1 at the top web level NN, and also they want us to know tau maxima. Okay, what is the maxima in this figure? Okay, now where is the neutral axis? The first step, just neutral axis. All right, neutral axis, A equal to sigma AI. There are two A here. The first one is B times H minus H1. Okay, top fringe, and then TH1. Okay, so sorry, I should write down first. Okay, this is B equal to 100 millimeter. All right, and this is H1 equal to 176 m. Okay. Okay, so this is H1, 176 mm. Good. Okay, and the second one is H equal to 200 mm. All right. Okay, so the total height 200, and T, what is T? T is T equal to 24 millimeter. Okay, so this is the problem. Okay, given by the problem. All right. So two area, this one B times H1 minus H1, H minus H1, and T times H1. Okay, two areas, sum them up together. It should be 100, 1200, 200 minus 176 plus 24 times 176 equal to 6624 millimeter squared. Okay, so A already here. And then we are going to determine the centroid of this T shape, right? So remember that because we are going to determine the coordinate of the centroid. So the first thing we are going to do is we set our own reference coordinate. You can set everywhere you want. However, remember that previously we said we recommend you to set at the either top or the bottom. This time I choose bottom. Okay, I choose bottom. And we also know that the y-axis must, at the middle, right? Because this is symmetry, right? So this is y. Okay, and we said this is AA. The AA line axis is arbitrary. We set this arbitrarily. Okay, no preference. I mean, make it bottom or top. This time I choose bottom. All right. So QAA is sigma YIAI. Okay, so H1 plus H minus H1 divided by 2 and times B H minus H1 plus H over 2 TH. Okay, so what does that mean? H1 plus H minus H1 over 2. What is that? It is actually this. Okay, so this is the first area. It's a, what's that? Centroid of the first area. And the coordinate of this is this green distance. The green distance is H1 plus, H1 plus the thickness half. So this, all right. Then times B times H minus H1. So this is the A, right? This is the A. A1. Okay. What is the A2? Sorry, it should be 1, right? Then, okay. And the second area, TH1 times its own centroid. Their centroid is here, right? The second area, centroid is here. So centroid is here. Suppose it should be a pink, all right? Okay, so it should be half H. This area, the second area, half H. All right. Okay. So now after you've done this, you can obtain the value 822,912 millimeter 3. Okay. And QAA divided by total area A will be the T-shaped centroid coordinate. Okay, so it should be the central, the neutral axis, Z. How can we obtain this? We know this Z axis to the bottom should be C2, right? So our C2 equal to QAA divided by total area A equal to 12423 millimeter. Okay, so you know why I choose AA at the bottom, because when we determine the centroid of this T shape, it will automatically tell the coordinate of this centroid, and then this centroid coordinate C2 to the bottom will be the longest distance from neutral axis to the bottom. And of course, C1 will be H minus C2 equal to 75.77 mm. Okay, so neutral axis, we done that, and we know the P. This is C1. C1. Okay. Yeah, that's it. So we successfully set the Z axis, okay, by determining the centroid of these two shapes. Finally, or not finally, secondly, we are going to calculate moment of inertia. Inertia, IZ. Okay, IAA equals to, okay, IAA. Now we need to do IAA. Okay. It is really interesting. Okay, we are going to determine IZ, right? Why I'm using IAA? This is a trick. Okay. Right. So when I told you, parallel axis theorem can only move from the centroid to other axis, right? But this is really weird. To do this, you can do this area and move to here, and you can move this central area and move to this. You can do that, and you can go back home. I encourage you to do that. Okay, or there's the interesting solution 2. Okay, I'm going to introducing solution 2. Interesting. We are going to use very similar negative area way. All right, I will draw that and you will understand. This is the first area, positive area. And then the second area, wow, is here. This green area is negative, all right? And then I'm going to determine the I about IAA. Maybe you'll think, why I need to IAA? I want IZ. Well, wait a moment, all right? I do IAA first, because green and yellow shape share the same axis at AA. That's the reason why I choose IAA first. BH3 divided by 3. You know, if the edge is at the, if the axis pass through the edge, BH3 over 3, right? Not 12. B minus T and H1, 3 over 3. Because they share the same axis. 1 to 8.56 times 10 to 6 millimeter 4. Okay, so maybe you will think, why I'm going to determine IAA greater than IZ? You can see that the IAA is the answer, the result of applying of the parallel axis theorem. We pretend we know IZ, and then we move to IAA by using parallel axis theory. So IAA is our answer, and IZ is actually our unknown plus AC2 squared. So IZ will be 26.33 times 10 to 6 millimeter 4. Okay? So here I'm going to use Chinese again. Okay? 好，这边我想要跟大家解释的哈，就是我们要算的是这一个 T 型的I 嘛哈，那 I 当然就是要对于它的中性轴来转，没有错。那可是啊，你会发现，你一开始如果要算的话，当然你没有问题，你可以先把这一个的中性轴移到中间去，这个没有问题。然后这个的中性轴移到这里去，然后把它加起来，可以。好，你可以回家试试看。这是 solution one， 这比较简单。我觉得这比较难，但是这比较系统性哦，就是怎么样做都对哦，但是就是有点麻烦而已。但是现在这个你可以看到这边有一个 trick 提供给大家做参考，就是说，还记得我们刚刚的 IZZ 可以用，就是那些 I 可以用负的面积来去减嘛，可以哈。所以你看这边有黄色的去减掉绿色的，可是啊，你要看看哦，我们的黄色的跟绿色的它共享的那个轴是哪里啊？是这里，对不对？他们就是如果你今天要他们怎么讲？如果今天绿色的话，它看它中间其实是这里，黄色的话是在这里高一点点，所以你不能同时的去计算它相减，你不能绿色的是算这一轴，黄色是算这一轴，然后相减，这样不对吧？你们要减的时候要是同一个轴啊，对不对哈？所以说绿色跟黄色的轴共享的是谁 ？AAA 轴，所以我们就利用这一点，我们就把黄色对于 A 轴的旋转是 BH3次方除以3，这个除以3表示说这个轴是贴在它的边界上。如果是在行星轴是12，对不对哈？那 B 减 TH1 也是绿色的这一段，它也是贴在边边上，所以它也是除以3。当你算出来这个东西，而是相减嘛，因为它是负的面积，减完以后 ，OK， 这个 T 型对于 A 轴来转的话，它的 I 是这么多。但是我们不是要 IAA 啊，我们是要 IZ， 对不对？我们可以因为 IZ 是它的行星嘛，那行星可以去做平行轴定理，对不对哈？只是这一次我们平行轴定理的未知数反而是在这里，而不是在这里。原本是在等号的左边，现在我们先算出了 IAA， 我们可以想象说它是从行星移动到 IAA 的之后的结果。好，所以 IZ 反而是我们的未知数了，所以我把 IAA 这边带进来 ，A 也算出来了嘛，哈 ，A 在这里 ，C2 在这里，带入进去以后，你的 IZ 就可以算出来。也就是说，我们是反过来使用平行轴定理 ，OK？ So, yeah, you need to be careful, all right? So this part is actually green part, and this is yellow part. Okay, and both of them are for IAA, rotate about AA, but the IAA is not our goal. Our goal is actually IZ, which is from the centroid. And we know that we can apply parallel axis theory from the centroid axis, right? So this IZ here, and we has the IAA result, so we can reversely determine IZ is this one. All right, so that's a little bit, you need to be careful about this. All right, so here, question 1. Tau 1. So tau 1, now we are ready. IZ and the neutral axis, we all done that. So now we are going to determine tau 1. Tau 1 equal to VQ1 divided by IB. So what is Q1? Q1 is actually the area of this, right? So the MN, the tau 1 is here. We want to determine the area above it, Q, okay? Now, VQ1 equal to B times H minus H1 times C1 minus H1 divided by 2, all right? And V is 45, and 153 times 10 to 3. And this is 26.33 times 10 to 6 times 24. Okay? Wait a minute. IZ T 24 Q B 45 24 T. Yeah. Right. So you can notice that the T here, IB, yeah, but IT 啦 sorry, IT 啦。It's T. Yeah, no wonder I feel weird. Okay, so remember the IB, this B, VQ divided by IB, okay, is the B here is not this B, it's actually T. Okay, you can see that, here we said, let me take a look. Q, yeah, you see this area, the T is actually the width of the web. It's not the bigger width. All right, so you can see tau VQ divided by IT. T is still small area. 好，你这边会发现，虽然我们在背公式的时候是 VQ 除以 IB， 对不对？那个 B 是因为我们是在做这个长方形嘛，长方形的 B。可是问题是我们现在的这个 tau 是在着重在 web 上哦，这个 web 长方形是它的宽度是 T 哦，不是这个的 B 哦，所以这边要小心。虽然它题目我们的背的上面是写 B， 但是这个在这边的 B 不是这个 B 哦，是这个 T， 听得懂吗？就是我们之前在背公式的时候是 VQ 除以 IB， 那个 B 是整个长方形的宽度。那现在我们在 Web 的时候，我们的宽度已经变成这么窄了，所以我们的 IB 的 B 其实是它的宽度是 T 哦。那所以这边虽然它的符号变了，请各位同学要记得它的定义是多少。Okay, so now here you see VQ1 divided by IT. Okay, IT. So this T is 24 rather than 100. Okay, you need to be really careful about this. Okay, so if you can accept that 10.9 m part. Okay, so this is tau 1. Right. Next is tau max. Okay, this is kind of tricky, tricky. Tau max. So if we want to get tau max, we need to get Q max because V is equal to previous one, right? I equal to the same, T equal to the same. So we want to get the tau max, we need to get Q max. So what is Q max? Remember, our shear has maxima at centroid, right? Neutral axis. So Q max supposed to be this one, right? This one. So Q max should be this one. So how to determine that? We can do this area times this distance, and also plus this area times its centroid to this distance. So you can get Q max by this method. Okay, this is solution 1. I will provide in solution 2. We can just do very interesting. Here. Do you see that? We can just use this Q, okay, and also this distance. You will see that you can feel free, go back to check. You can use this shape and you determine Q max and you check with what I gave you now. It will be exactly the same. Okay, it's really fun. Okay, T times C2 times C2 divided by 2. So this is the pink region below. The pink region below Q is actually equal to the T shape above. It will be exactly the same. Why? Because Q is actually the area distribution, right? So below the Z and above Z, Q should be exactly the same, right? So you either do this twice for 2 area, or you can do it smartly. You can do more clever way. You choose bound below and then do this. Will be exactly the same value. All right. You can go back home and to do the check, and you will understand what I'm talking about. 听得懂吗？就是说我这个 Q 啊我要算 tau max， 其实是为了要算，要什么？要算 Q max， 因为 I 啊、T 啊、V 啊都一样，在这截面积上。那怎么样得到 Q max 呢？你有2种做法。第一种做法是算上面的 T 的 Q max， 然后要怎么算呢？这个面积乘上它的距离，它的行星到中心轴的距离乘起来，再加上这个小面积乘上它的行星到中心轴的距离加起来，那就是这 T 的 Q max。但实际上，下面这整个的面积乘上它的行星到的中心轴距离也会一样哦。为什么？因为我们说过，我们的 z 是中性轴，是行星嘛。行星的定义是什么？定义是面积对于这个轴的平均的分布的状态。既然它已经画了这一条线，表示说上面的分布跟下面的分布会是一样的，那你上面算出来很累，你不如就算下面就好。所以我这橘色这个 T 乘上 C2 它的面积，然后 C2 除以2是它这个高度的1半，那就正好算出它的 Q max。然后你可以算上面的 T 的 Q max 是不是会跟它一模一样？你回家可以试试看。All right, so we substitute Q max. VQ mix and divide by IT, IZT, IZT, and equal to 13.2 megapascal. And you can check, yes, it actually greater than the tau 1. Yes, which means that we are correct. Okay, so this is a really difficult example. And I would prefer you to check that. And that's it. That's the most difficult example in chapter 5. All right. Congratulations. You've done it. Hey, 请问 Yeah, you are right. H1, right? Thank you. Please tell me your number. 111 613 006. Good. Any questions? Okay, sure. Thank you very much. That's S1, H1. 超难哦，这个我小时候就觉得哇，这东西在干嘛？讲超难的。而且我们那时候老师都直接就说，哎呀，来算哦，来算 Q mix， 然后就算下面。然后我想说，为什么要算下面？为什么不算上面？你不是说要算上面吗？要算上面。然后我想了好久，而且应该说我是最近要在教，就是我在当了老师以后，我才回去想这个问题，然后在想，哦，原来它的 Q 应该是它是平均分配的哦，上下会是一样，所以当然也有可能是我以前没有专心听课啦哈，但就是我也是在这开始要教这门课的时候，才真正去思考这个问题，就是为什么 Q mix 你算上面跟下面都一样。然后我之前也是小时候我也就觉得说，为什么切一刀，然后留左边留右边都没有关系？我小时候也不知道为什么，然后算对或算错都是碰运气的。但其实发现，哎，没有，你留哪边都可以。那也就是说，小时候就不求甚解，长大以后就是为了要教别人才会真正去思考，怎么对什么样，就是它其实是通用的，或是等效的。那昨天我也去听了一个机械系老师的演讲教学分享，他们就有在教，就是说公数，他们就是把一个课题热传拆成5个等份，然后给同学自己去念，然后后来大家再互相教这样。然后我觉得这好像也是蛮好的方法。当你要去教别人的时候，就会怕说，哎呀，别人都会教我了，我不会教别人，就会积极的去学习。所以我觉得这种教学方法好像也是蛮不错的。对，当你要把知识教给别人的时候，跟你自己去吸收，好像是不太一样的哦，这还蛮不错的一个想法。All right, final topic. Final topic is, well, it's not really difficult. All right, so kind of combining everything from chapter 1, 2, 3. Okay, sorry, just 1, 2, and 4, 5. All right, 3, well, not here. 3 is too difficult. 3 is distortion, so it's not. So the distortion is not symmetry, right? Y symmetry. Torsion is not symmetry, right? According to the definition in the beginning. 还记得第5章我们说我们的力都是对称于这个 Y 轴的吗？所以如果你今天是第3章的 torsion 的话，它是照着这个转，那就不对称啦，所以不能结合在这里。Okay? But chapter 1 and 2, normal actual loading. Yeah, actual loading is actually symmetry to the Y, so we can combine together. So it will make everything even more complicated or even more fun. All right, next page. Next page, being with excess load. Okay, so actually this is chapter 2. So for example, this is an example, right? the example has the being with fixed end. And the fixed end, and I will give you a axis, all right? The axis is x. Axis is y, y here, all right? So this is side view, okay? Side view. And because this is a, so you will have a force, oblique force, which means that you have Q, and this is S. So, sorry, I should make it. Wait a minute. Can I do it? Okay, I make it dashed. All right, dashed, dashed, dashed. So which means that the Q and S, the component of the P 分量. Okay, and you can have the reaction force at the fixed end. So you will have how many reaction force? R, H, R, V, and also N, no. Okay, so you will have 3 reaction force for fixed end. And then you can draw the shear moment diagram, right? Shear moment diagram. 0 and V and N. 0 M. All right. And the answer is V always negative, and M is actually a decreasing M. All right, that's it. So let's take a look. If we are going to know the force in the material, okay, at the cross section, all we need to do is cut, right? We cut. Okay. Okay, so if we cut it, and we leave the left-hand side, okay, we leave the left-hand side, and you see here is the V, and here is the M. We know that this is a chapter 4 sign convention, right? Now, be careful, because now we have the S, chapter 2, right? Chapter 1 and 2. The S is the axial load. So we have one more thing. N. Remember that? N. So you can say, okay, M here equal to Q times L minus X. Q, okay, Q is here, okay? Q minus L minus X. So this is X. If we cut at X, and the entire length are L. This is X equal to L. All right. This is X equal to L. Okay. So M equal to Q times L minus X. You can see that the minus X means that this is negative slope, right? Negative slope. Yes. And so M, yeah. How about V? V is minus Q, okay, minus Q. So no problem, okay? And N here is S. N equal to S. N equal to S. No problem, right? N equal to S. If you don't understand, okay, you cut it, right? You cut it. And you leave left-hand side, your RH must be at this, okay? Because RH and S are balanced. So RH is here. And RH equal to S. So your S equal to N. All right? So no problem. And please be careful. This two equation is chapter 4 and chapter 5, right? You know that. And this is chapter 1 and 2. N equal to S. And your stress, again, stress, sigma equal to minus ny divided by I, and tau equal to VQ divided by IB, of course, chapter 4 and chapter 5. Sorry, this is only 5. Only 5. Okay? And sigma equal to N divided by A, right? So this is chapter 1. Okay? So now, remember that our chapter 5 will give chapter 1 will give you normal stress. Chapter 1 will give you normal stress. Okay, sigma equal to N divided by A. So this, if you have a actual normal stress, you will have this stress distribution. Sorry, I should give you a 10 minutes break. Yeah, I see 1 minute. So 2 minutes. So I will see you at 32. Okay, 4:32. Okay, sorry. And if you have any questions, come here.有问题吗？下第一个期末考周对不对？我怎么觉得我会教不完？不过好在就是说大家人数很少，10个人左右下，所以大家的时间应该会很好抢。所以我在想，我认为我在期末考周可以教完，我猜的。所以那接下来就是你们爱什么时间，期末考的什么时间？怎么样？你们想要在下个礼拜的期末考的礼拜2考试吗？同一就是我觉得现在没办法，就是6月1号、2号是第一周嘛，期末考周的下一个周末的礼拜，下一个周的礼拜2考试，可能应该是没有问题。OK，又或者是大家觉得说我们想要挤在期末考周，那我就是礼拜3教完，可以礼拜4考，礼拜5考都可以，看大家，我没有意见，这样大家觉得怎么样？可以走 OK 吗？也就是期末考周的下一个礼拜2，也就是第17周嘛，对不对？OK，礼拜2，那样会是几号啊？10号。OK， 很棒。好，好，就这样。下一个是 That's things. OK, welcome back。感觉好像没有怎么下课，我去上个厕所，我去拿个包包，走回来，哎就结束了。哇，时间过真是有够快的。哎，好，就这样。Let's continue. Okay, because I don't know if I can make it. I mean the progress. Can I finish in time? I hope I can do that. All right. So chapter 1 give us sigma equal to n divided by a. So because the point load here will make, typically it will make the uniform stress in the material, right? So you can see this uniform stress distribution. So this is n, well, resulted by, just due to n, and this is due to m. All right, what is m? Remember, or maybe you are not recognizing this shape, but if you plot it in another way, you will understand what I'm talking about. Okay, remember, it's just because this is to the left-hand side, so it put to the left-hand side, okay? But actually, if you put it right-hand side with different arrow, different direction, you know, actually, this is due to the moment, right? Due to the moment. So moment is actually due to this, okay? So, with the beams with actual loads, typically will result into plus equal to 3 possibility, all right, resulting in 3 possibility, 3 possibilities, okay? So if the n is bigger, it's really big, it will push all the negative to the positive way, okay? Or the n is not that just equal to the minus n, minus stress due to the n, it will has a triangle shape. Or the n is not really good, not really big, no more stress. The minus compression due to the m still valid. Okay, so it will twist the area of the distribution. Okay, so 3 possibility. Okay, and you will see that sigma total, all right? I should say total, because this sigma is actually this one plus this one, all right? So n divided by a minus n1. Okay, so sigma plus sigma becomes sigma total, all right? Sigma due to n, sigma due to n, okay? Sigma due to the moment, sigma due to the normal stress, normal load, sorry, normal load. And you can get sigma total, n divided by a minus ny divided by I. Okay, so that's it. No new things introduced in this page. All right, they are all old things we have taught that before. So don't worry about it. And just combine them together. And then combine them together, you can get the next example. Next example. Wow. Okay, I will give you the questions. First, here is X. Here is Y. So you can see that this is side view, and this is point A. And point B. Okay, and the distance is L divided by 2 equal to 750 mm. And this is L divided by 2, 750 mm. Okay. Then this is the middle part, neutral axis actually. And the distance between this is D 140 millimeter. All right. And there is a load. There is a load acting obliquely. All right. P equal to 4500 M. And the component, horizontal component, P sine 60 degree. And downward, P cosine 60 degree. All right, so this is the problem. Okay. Oh, also the section, cross-section view. Cross-section is a hollow square shape. You see Y and Z. So this is cross-section view. Here, this is 150 millimeter. Okay, this is B 150 millimeter. And this is really interesting. It directly tell you the area. Okay, and directly tell your I. So A and I here for this cross section, it has told you. Okay, that's good. We don't need to determine that. And it also a symmetry cross section. We don't need to determine the neutral axis. That's good. A and I also tell you. No problem. That's nice. P is 4,500. Okay, so again, find sigma T mix and sigma C mix. Well, that will be a little bit difficult. Okay, so I'm going to draw the chapter 4 things for you. All right, from here. So this is Y. Okay, and this is right. And so you can see that this is a real world problem. Okay, but now we are going to reduce into a chapter 4 problem. That will be a little bit weird. You can see that this is a pin support. So I give you a pin support, no problem. It's just a pin, right? Pin, so it can be rotated. It's okay. And here, wow, this is a little bit weird. You see, there's a pin. But why I say this is a roller? Because you see there's a this symbol. This symbol means very, very long. Very long. Okay, so which means that you have a really long bar. And you can see that if you have long bar, just like a, how to say that? It's a pendulum. 钟摆 ，OK? So you can kind of to the left, to the right, to the left, to the right, but not up because you have the actual height. But because you have really long like pendulum things, you can just move left and right a little bit. All right. 这当然有一点蛮有趣的，就是它这边的非常非常长，非常非常长的一根吊在那里。那吊在那里可以想象它可以像钟摆一样那种左右摇晃，但是你却不能去把那个钟摆缩短啊，这种感觉，所以就有点像是 roller 的感觉。Okay, so again, let's take a look. You will see a. Oh, okay. So this is really important now. So here is how we transfer the middle part P things into the chapter 4 things. You can see this is PV equal to 2250 M, and this is pH. Uh, 3897N. Okay, and oh, this is really important. MC equal to 545.6 times 10 to 3 N times millimeter. Okay, so how can we obtain this? Let's take a look. So 4500 times sine 60, okay, 3897, no problem. And if you times cosine 60 degree, you got 2250, and okay, no problem. But you notice that we move here, we move this point to here. Actually, this is okay because the force can directly move along the axis, okay? But if you move that, you need to considering the moment, okay? You see, to this point, this P cosine 60 cannot offer any moment, but P sine 60, it does provide some moment because due to this force arm. This force arm make this P sine rotate about the point C. Okay, I forgot to write point C here. So you see this 545.C times 10 to 3 is actually P sine 60 times 140. We get 545.6 times 10 to 3. All right, so this times this, got that. All right, we need to be sort of careful. Okay, so now we can obtain here is RB, okay, and here is RA, and there is RH. Why? Because we have a TH in the horizontal, so of course the hinge will provide the reaction force. So now we sort of make this ugly real world problem into the chapter 4 simplified form. Okay, and we can start drawing the shear moment diagram. Shear moment diagram V0 and M. And interestingly, N, okay, this is actual load, actual force. diagram. Yes, let's take a look. You know how to draw V. V here and here. Okay, so here is 148.9 and this is minus 761 N. Okay, and there is a okay, and this hey okay. Well, I didn't pay too much time, too much attention here because chapter 4. Okay, you know that, but I will give you the answer. What is that? This is 1116.8 times 10 to 3 N dot NM, and this point is 571.2 times 10 to 3 N dot NM. Okay. Well, that's a little bit difficult. I will give you the soul of RH 3897 N and RA equal to 1489 N, and this is the RB equal to 761 N. Okay, so sorry, I forgot to tell you that after we draw this, we can do the force balance, and we can solve RH, RA, RB, that value, and with this value we can draw this. All right, so you see 1489, and 761, and yeah, that's it. And N here, N is 3897, right? 3897 and 0. Okay, so you see that because here pH at the middle, right? So only this part has normal stress. There's nothing here, no force. Okay, so 3897 only occurred here and nothing here. Okay, so that's a shear moment diagram, and you can go back home and draw by yourself, all right, practice by yourself. So after we draw this, we can go back to say, okay, what is the actual example asking? It's called sigma T max, sigma C max. The reason why we are going to determine N here, because N also affecting the sigma T and sigma C, right? Because remember, your normal will affect the final result of the compression, or tensile stress. Okay, so that's the reason why we need this. So now we are going to determine what is sigma T. Sigma T max. So where is the sigma T max? So you see, sorry, I skipped one thing. I forgot to mention this jump. Okay, this jump. Sorry. Let's go back to this jump. This jump is 116.8 jump to 5712, 1.2. Why? You can see that because okay, I draw here. If you have remember that you have a stress element, right? and this is M. So before you have an MC, the MC is counterclockwise, right? You're counterclockwise. So before MC, this is M. So what is the to the right hand side? What is the M? Your M must be minus MC so that you can balance, right? So if you're here and this is the happy curve, right? Happy curve, M. But if you have an MC here, which means that you are going to balance the MC to the right. So here, MC will make the M even counterclockwise. So you need to make the balance minus MC to balance this stress element. So they won't rotating. So you see, after the MC, your right hand side M moment should be minus MC. So that's the reason why it dropped. 好，这边忘记讲了一下，就是为什么它是往下降，不是往上升啊？其实这我第4章也讲过了啦，就是说原本你是 M 嘛，左边还没有 NC 之前你是 N 哦。假设你没有这个 NC 的时候，左边是 M， 右边也是 M， 开心对不对？就是一个开心的曲线。但是你现在多了一个 MC 在中间路途中，你多了一个 MC， 表示说，如果你今天右边不降下来的话，不减 MC 的话，哇，那这样子它就会开始一直转，往逆时针开始转。所以你右边这个左边已经固定了嘛，中间这是你施加的，你不能变，所以你只能变右边啦。右边 M 一定要减掉 MC， 它才会让这个东西方格是平衡在中间，不会乱转。所以你经过了一个 MC， 你右边一定要减 MC。经过了一个 counterclockwise 的 MC， 你右边这边一定要减一个 MC 去平衡它。那一减，当就掉下来了。OK， 它就不会升上去啊。所以这边是我忘记跟大家提醒，虽然我也以前讲过啊 ，Chapter 4已经讲过。好 ，So yeah, just kind of recall that something we talked about and discuss about the moment jump. Okay, moment jump. So yeah. Then let's continue. Okay, sigma T max. Where is the sigma T max will possibly occur? Yeah, you see, this is positive, right? This is positive. This is positive. So tensile must happen in here and here. Okay, so you see, it must occur at this position because this is biggest moment and biggest N. Okay, so no doubt. Okay, so NA minus MY divided by I. So 3897 divided by A 12500 minus what? Minus 1116.8 times 10 to 3 times, very important, 33.86 times 10 to 6 is I. So what is the empty space? Okay, 75 and minus, okay, because this is C2, sorry, it should be C2, it should be bottom, Okay, so imagine that at this point, okay, this point, it has the greatest moment, at this point, it has greatest moment M, and this is positive, so it should be make this, right? So you have make this M. So bottom must have the tensile due to the M, and also the N also give a uniform N. So you have this due to the M, this due to the N. So you need to sum them up together, and this the moment, positive moment will make the bottom tensile. So you should substitute C2. So this is minus 75. Okay, and you can get 2.79 MPa. So this is the answer. Okay, sigma T max occurred at this point. Okay. Next, this point actually slightly left to the center. Slightly left to the center. Okay, we have 60 maxima. How about 60? Sorry, sigma C max. Oh, left, and sigma C max right. That's interesting. Let's take a look. There is a debate for which point. You see, here, this has higher M, greater M. So it has the greatest compression on the top, but also has 3A97 to tensile. So it will kind of delete the effect. But now here has lower M, but no normal stress to cancel. So which one will be the maximum compression? We don't know it yet. Okay, so we need to figure it out. 听得懂吗？就是说你超过终点之前，你虽然有最大的弯曲，这个最大弯曲会给你最大的上面的最大的压应力，但是你的 normal stress 会把它拉回去，会有抵消掉的作用。但是下面因为超过终点以后，你的 moment 就变小了，变小是感觉起来会没有那么压那么重，但它也没有正向力去把它拉回来，它是0。好，所以两个有得比哦，不知道哪一个是大的。Okay, so that's the reason why we need to calculate that. All right, so we need to calculate 3A97. This is positive because this is tensile. 12500 and minus 1116.8 times 10 to 3 and 33.86 times 10 to 6. This time 75, and this is C1 because this is upper level. Now it's C1, positive 75. Okay, and now you get minus 2.16 MPa. Yes, it's still compression. Okay. How about sigma C max right? C max right has 0 normal stress, no reduction because 0, right? This is 0. Here, 3A97. Okay, and minus 571.2 times 10 to 3. times 75. And of course, this is 75 as well, because this is upper, right? This is the upper. Again, C1 as well, and this is also upper, because you are talking about compression, right? 3.86 times 10 to 6. So now result is minus 1.265 MPa. Okay, so which one is the winner? Minus 2.16 MPa. All right, so the maximal tensile and maximal compression all occur at the left of the center, just right at this point, right this point. And the top is compressional maximum. Bottom will be a tensile maximum. That's it. Done. Congratulations. Chapter 5. Done. The most difficult part. All right. 恭喜大家。哦，这真的是一个非常非常难的一个章节哦，但很有趣的事情，它叫做 Being Basic 啊、还有 Chapter 6的 Being Advanced， 哇，那真的是难到爆。那就是这样。那 So next next Wednesday will be our quiz. All right. Quiz 2. Next Wednesday should be 28th of May. Is that correct? 28. 28? Wednesday, right? Well, so tomorrow is 21, yes. And start from 9 o'clock. And suppose it should be like last time. I can you may finish before the course, and I will give you more lecture. Okay, so please tell everyone. Okay, quiz 2, 28th May, Wednesday, 9 o'clock. So thank you. This is really difficult, I would say, and I hope everyone can know what it is. Okay. And next one, chapter 7, will be our last chapter in this course, and it will relatively easy. Okay, not that difficult anymore. I hope everyone can. Oh, right. But the chapter 7 is the most important chapter for material science engineering department, right? In other university like University of Oxford, okay, or in the UK, they has its own lecture called stress and strain analysis. One lecture, entire lecture, just talk about this, okay? But in this department, we only have one chapter. This is a little bit weird, but well, next, all right, next one. Chapter 7, analysis of stress and strain. This is one course, entire one course in University of Oxford. OK， 我在以前英国念书的时候，这个是一整门课哦，但是那边只讲了一章，有点可惜。But this is really important for material science engineering. All right, the most important part is this, because you will know the general idea of stress and strain in the material. Wow, that's really difficult. Oh, well, not difficult. This is relatively easy compared to chapter 5, but this is really important. And it will be used in, wow, anywhere in the material field, even in TSMC, in your company later, or anywhere. Okay, so again, because we are talking about stress and strain, we must talk about stress element. Because when we talk about stress element, we actually talk about the material point in the material. Okay, so you can see that when we have a M moment and the shear, we will generating the stress distribution, either normal stress, either shear stress. Okay, and you can notice that my shear stress is biggest at the neutral axis and less at the bottom and top. So you can imagine that this stress element can be drawn. You can see sigma equal to minus MYI divided by I, tau equal to VQ divided by IB. So you know sigma and you know tau. What is sigma? Sigma is normal stress. Tau is shear stress. So you can see this. We take it here, and this area. So this area will be this area. All right, can you see that? This area will be this area. All right, so your sigma x, tau x. Oh, also, when we talk about stress element, now we will follow our previous sign convention. Okay, so if you have positive m, you will make this sigma x minus because it's compression, right? And tau xy, if you have the positive in shear moment diagram, you will have minus tau xy in this chapter. So you will be careful. 看这边有点小心哈。你们看到我们不是说简力弯曲图的 V 跟 V 会跟一般的正负号有点相反，对不对哈？你看我们这边的 V 正在简力弯曲图是正的，对不对哈？可是它会是往下。那如果往下，我们来看，如果在这边的话，哎，还记得我们那时候在讲第2章的时候的符号吗？它是这边如果是往下，反而是为负哦。好，然后这边 sigma x 在这边是压的话，加进去的话 ，sigma x 是负的哦。好，所以说这边要小心，就是我们在画 stress element 的时候，我们的正负号就回到我们的第2章的时候教的东西啊，所以这边有点需要大家注意的。Okay, and now if we cut this element out, it becomes 3-dimensional, right? 3-dimensional. So now we can define this x, y, z axis, all right? And we will define this area sigma x tau xy and sigma y tau yx, and we will explain this later in more detail, all right? So this is 3-dimensional, but if we just see it's in 2-dimensional, okay? Because we are not talking about any component along z. We are not talking about along z component, right? So we can make this 3-dimensional in the flat way. Okay, we don't consider z component. All right, easy. Okay. And now, previously we said we know the proper x, proper y element. How can we make stress transformation if our focus is in different plane, PQ, we have a theta angle, x1, from x to the x1. How can we make the stress transformation? We want to know the new component of the sigma x1, new component of tau x1, y1. Can we do that? Yes, of course we could. And we did that actually. So the stress component are different due to the orientation, but the stress state at the point remain unchanged. This is really important. Actually, I mentioned this quite so many times. Here, the stress state, the stress condition are all the same because we are talking about the same material property, same material point. The reason why we will have different value is actually because we choose different coordinate. So if you have a different coordinate, you will have different component value. But just like a vector, you change the coordinate, you change the component, but the actual vector value will be the same. All right, so this is really important. Now I'm going to give you a stress representation. This is really important, okay? Now, the normal stress we typically call sigma x. You know that. You see that quite well. You know, okay, this sigma x, this is sigma x, positive x direction, and in the positive x phase. And then you have positive convention because it has tensile. Tensile will make it positive, no problem. It's normal stress, sigma x. But actually, in other lecture class, in other university, okay, or other textbook, we typically call x, or we will call it sigma 1, 1. Okay? Because x equal to 1, y equal to 2, z equal to, well, I shouldn't write down equal, sorry. I should say x, we're using 1 as a representation. 2, 3. Okay? So when you say 1, 1 is x. Okay? And the first x is the plan. Okay? And the second x is the direction. Okay? So you see, this is x plan with the normal along x. All right? And your direction is also x. So sigma x. So when you are normal stress, you definitely has repeated index. When you x, y, it must be normal to that plan. Okay? So you can see it here, sigma x. You should have sigma y. So in this textbook, for simplicity, to make it easy, we just reduce the second repeated index, becomes sigma x, sigma y. Okay? But in other textbook, it typically says sigma 1, 1. All right? Now, next one. Very important. In our textbook, we said shear stress, we're using tau. Again, tau x means the plan. Y means the direction. Okay? And in other textbook, in other textbook, we are not saying tau, we say sigma. Again, so maybe you say, hey, why? If you're using sigma, will you be mixed, confused with normal stress? No, because x equal to 1, y equal to 2. You know, this is sigma xy, sorry, it's sigma xy. Okay, so you see, this is x plane, y direction, x plane, y direction. It must be a shear because you know the value are not the same, not 1, 1, not 2, 2, not 3, 3. This is 1 and 2. So which means that the direction must align on that normal, on that plane. So it must be shear. So actually, tau symbol is useless. So from now on, well, after you graduate this course, pass this course, you can name the stress, no matter this is normal or shear. You can always name it shear because you can identify it is the shear or normal by the index. 听懂我在讲什么？哦，听得懂哈？就是其实啊 ，stress 都用 sigma 就好了啦，没有人在用 sigma 跟 tau 的啦，因为你只要用下面的标注，你就可以知道它到底是简力还是正向啦。正向就是面跟方向是一模一样 ，x x y y z z。那如果是用数字的话，就是1 1 2 2 3 3。那如果是1 2，那表示说在这个面1的这个面上，你的方向是2，那一定是躺在那个面上嘛，所以你就知道它是 shear 了哦，所以非常简单。那正向、负向就都知道了。Now I'm going to tell you 1 2 and 1 1 and 1 3 or 3 3. That's called tensor. Tensor. Okay? Tensor in Chinese, 张量。学长姐 call them, senior call them 天书啊，因为听不懂、看不懂，因为超难啊，真的是这样，所以很难。但是当你一旦学会以后，一切都通了啊！谁发明的？爱因斯坦发明的。哦，聪明，太厉害了。Tensor is really cool things because the tensor is actually represent for everything, just like a matrix. Matrix is second order tensor. This is a matrix. Okay, if you only have sigma v1, this is vector, only one dimension. Okay, so this is a really smart representation symbol. So yeah, be careful. And also, I remember I told you how to determine the positive or negative of the shear stress, right? So remember that positive x surface and positive y direction, positive times positive, positive. Here, negative y surface, negative x direction, negative times negative, positive, still positive. All right, so that's how I did it. Now we are going to, tomorrow I'm going to introduce plane stress. What is plane stress? Plane stress is we only talk about stress on XY plane, no stress on Z axis. So everything will be easy, okay? And I will give you an introduction, proof, and the proof also fall in 95% of proof in mechanics of material, which is stress times area equal to force, balance, and you can get a result. All right. So thank you very much. I will see you tomorrow. Thank you. If you have any questions, just come here.